Hey, hello. In this lesson, I'm going to show you some tricks or some ways to dictate the types of hybrid, the geometry, the magnetic nature, and the type of orbital complex in a coordination compound using the Valent Bond Theory or the VBN in short. Even though the theory has its limitations, but we are going to talk about the limitations in the subsequent lesson. So let's check it. But before going into it, it will be nice if you have a little knowledge on the calculation of oxidation state, writing of electronic configuration using the SPDF orbital, and also a little knowledge about the spectrochemical series, which is the arrangement of ligands based on their splitting abilities. Alright, I've written some few steps here to follow. And from the steps, the first step here is to always find the oxidation state of the central metal. After finding the oxidation state of the central metal, we're going to identify whether the ligand is a strong field or is a weak field, as we are fully aware that the strong field ligands always force pairing of electrons, and those weak field ligands don't force pairing of electrons. Then lastly, we're going to draw the electrons in their orbitals, right? And on the right hand side here, I have the strong field ligands. You can see them, and we have the weak field ligands. I'm going to show you how you're going to apply them, and you will see why we have to know whether it's a strong field or a weak field ligand. So I'm going to use an example to solve a problem. After solving the problem, we'll be able to identify the geometry, the hybrids, and probably the nature of the complex.
Okay, using this complex as an example, we have copper with 6 fluorine 3 minus. Now we're going to calculate the oxidation state of the central metal, which is the first thing to do. So in order for us to calculate this central metal, the copper, we're going to equate it to this -3, because that's one of the rules of calculation of oxidation state. We're going to equate it to the charge if it is an ion. So we're going to say copper plus -1, which is the oxidation state of this fluorine, times 6 is equals to -3. So we have copper plus into -6 equals to -3. So this negative, positive times negative, in mathematics is going to be -6 equals to -3. So we have copper equals to -3 plus 6. Therefore, we say copper now is going to be +3. So this is the oxidation state of the central metal. Now, what is the implication of this? We know that when element gain positive charge, that means it has lost or it has donated an electron. So the number of that charge is equal to the number of the electron donated. So copper is having +3, that means it's going to donate 3 electrons. It's going to lose 3 electrons. So we're going to draw the electronic configuration of copper. We know that the atomic number of copper is 27 on the periodic table. So therefore the electronic configuration is going to be argon 3d7 4s2 4p0 and 4d0. So this is the normal electronic configuration of copper. But remember that copper is +2 now, because it's going to lose 3 electrons. So losing the 3 electrons, we're going to remove the 2 electrons from this 4s orbital, then 1 electron from the d orbital, making it 6. Therefore, the new electronic configuration of copper in this case is going to be argon 3d6 4s0 now, then 4p0 and 4d0. So now the next thing we are going to check is the type of ligand, that is this. What type of ligand is this? Remember, in our introduction we said that we have 2 types of ligands, and we're going to see fluorine is here. Can we see it here? That is a weak field ligand, and we know what weak field ligands can do and what strong field ligands can do. We said that strong field ligands always force pairing of electrons. Now, since fluorine is a weak field ligand, that means it's not going to force pairing. So let's draw the orbital. As we know, orbital is a region in space where there is high possibility of getting an electron. So let's draw it and see. So drawing the orbitals now. So the first one is 3D, which is always having the maximum of 10 electrons. So we're going to have 5 boxes. So we have this 1, 2, 3, 4, 5. This is the 3D orbital. Then we have the s orbital, which is usually only a box because it takes the maximum of 2 electrons. Then we have the 4p, which takes the maximum of 6 electrons, which is always 3. 1, 2, 3. Then we have the 4d, which takes the maximum of also another 10. 1, 2, 3, 4, 5. So this is 4s, this is 4p, and this is 4d. Now remember that we have 6 electrons, so we're going to enter 6 electrons singly before pairing. So we have 1, 2, 3, 4, 5, and 6. So this is the orbital and the electrons of the central metal. Now remember that our complex is having fluorine as the ligand. This is the ligand in this case. The ligand is this, is fluorine. And in our first introduction, we saw that fluorine is a weak field ligand, so it's not going to force pairing of electrons. Remember that it's only strong field ligands that force the pairing of electrons. So if that's the case, this is what's going to happen. This fluorine, 6 of them, it's not going to force this electron to pair up, but rather it will prefer to enter these orbitals. So we have six pairs of electrons from fluorine. We have 1, 2, 3, 4. We have 5, 6. We have, so 6 pairs, 1, 2, 3, 4, 5, and 6. So that is it. Now this is, remember, fluorine, 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 and fluorine. Therefore the new configuration of the complex now is going to be something like this. We're going to have like this: 1, 2, 3, 4, 5. That's the 3D. Then we have something like this: 1, 2, 3, 4, 5, 6. This is 4s, 4s, which is in another way we don't need to write the 4. We can just say S P. How many P? 1 2 3. SP3. How many D? 1 2. D2. So this is the new hybrid. Then we have the remaining boxes, which is 1 2 3. So this one here is going to be 1 2 3 4, like this. This one here is going to be something like this, and like this. Then this is our 4D. Can you see? So this is our new hybrid. This is our new hybrid, SP3D2. So from this one here, we should be able to derive some information. So what do you think is the magnetic nature? Magnetic nature. Remember that magnetism is due to unpaired electrons, and we have how many unpaired electrons? 1 2 3 4. So there are 4 unpaired electrons, therefore it's going to be paramagnetic. Paramagnetic. Can you see? Paramagnetic. If these electrons were paired, we would have been diamagnetic, because paramagnetic magnetism is due to unpaired electrons. Then we have already seen that the hybrid is P3D2. Then the geometry is usually any complex that you have this kind of hybrid, it is usually octahedral. Right? Then finally, what type of complex is this? We can say is an outer complex. Outer, say, type of complex. Outer ligand complex or outer complex. Why? Because these electrons did not go into the 3D orbitals. This 3D, we can say that is the pure metal that is here. If this fluorine paired into this, would have been an inner complex, but because these are pure metals, the orbitals are still occupied by the electrons of the metal, is going to be outer complex. So our second example, we're going to use this complex. Cobalt again, but in this example, our ligand is ammonia. This one is +3. Or we can write it this way, +3. Now, calculating the oxidation state of the central metal, we know that ammonia is 0, so it's going to be cobalt plus 0 times 6, right, equals to +3. So it's going to be cobalt plus 0 equals to +3. Therefore, cobalt is going to be +3. Still going to lose 3 electrons from its orbital. Drawing the writing the electronic configuration is still going to be the atomic number of 27, which is argon. Then we have 3d7, 4s, 4s2. Then we have 4 P0 and 4D0. So removing the electrons, we're going to remove this and remove this, remains 6. So in this case, we're going to have 3D6, 4S0, 4P0 and 4D0 in this case. So drawing the orbitals now, we're going to have something like this. Have something like this. 1, 2, 3, 4, 5. This is 3D, the 3D6, 3D6. Then we have the 4S. Then we have the 4P. 1, 2, and 3. This is 4P. And lastly, we have 1, 2, 3, 4, 5. That's the 4D orbital. Now, remember that we're going to check what type of ligand is this. This is, so let's see, this is actually, let's see, can you see there? It's a strong field ligand. That means it's going to force the pairing of the electrons. So in this case now, we're going to have something like this. We're going to have something like this. 6 electrons will be 1, 2, pair them at the same time. 4, 5, 6. So leaving 2 empty space. You can see that in our first example, we didn't pair them. We entered them singly before pairing them. But in this case, since it is a strong field ligand, it will force it to pair first. So creating 2 vacant orbitals for in the d orbital for the ligand to come in. So therefore, now we'll have. So let me use a different color here for better understanding. We have 1, 2. We have 3, 4, 5. 1, 2, 1, 2, 3, 4, 5, and lastly 6. So this one here is from ammonia, and these are our new hybrid. Therefore, we're going to draw the shell now. Sorry, the orbitals. We're going to have something like this. We're going to have something like this. Then we have something like this. 1, 2, 3, 4, 5, 6. Then we'll have 1, 2, 3, 4, 5. So this is our 3D6, but this will be our new hybrid, which is what? Which is 2 out of, can you see, 2 out of this, 2 out of this 3D is going to be D2. Then we have 1S here, can you see it? So we have S. Then we have 3 of the P, so we have P3. So this one's here, like this, like this, like this. This one is fill up. Then we have this one here. So now in this case, we'll the question that we're gonna ask is, what is the hybridization? Hybridization is actually D2sp3. Geometry. Geometry is going to be still octahedral. And lastly, what do we think is going to be the magnetic nature? So check it. Is there any unpaired electrons? This one, there is no any unpaired electron. Therefore, it's going to be diamagnetic. Because paramagnetic is unpaired electron, but it is all the electrons are paired. Therefore, is diamagnetic. Alright, before finishing the lesson, I'm going to give you like two complexes. Try them and see how you can get the magnetic nature, the geometry, and the hybrids, right? We have the first one is something like this: iron with Cn 6 minus 4. The second one is Fe. We have 6 here. This one. So try it and see how you can get the geometry, the magnetic nature, and the type of hybridization. Thanks for watching.